So in the previous video, we introduced this concept, this theory of Vesper, which states that we can determine the electron and molecular geometry of a molecule when looking at a Lewis dot structure and determining number of bonded groups and lone pairs of electrons. And so the types of Vesper notation and molecular and electron shapes that you will encounter in your online homework and in the exam, I have summarized here. And you may think, oh, there's a heck of a lot of information here, and there is. I put this information particularly about the electron geometry here because you will need that information for the online homework. But as I mentioned in the previous video, and as I have as a star down here, for the exam, you do not need to memorize the corresponding electron geometry with a Vesper notation. You just need to know the corresponding molecular geometry. So I would recommend, as part of your study practices, getting a bunch of flashcards, a bunch of 3x5 cards. On one side of the flashcard, you could write AX2, and then on the other side, you could write the molecular geometry linear. It's really these two columns that you need to commit to memory and also be able to use to answer questions about a Lewis dot structure. So we introduced this generic Lewis dot structure in the previous video, AB3. We said it's Vesper notation. I've got 3 bonded groups and 1 lone pair. So my Vesper notation, make my little pointer, my Vesper notation for this molecule would be AX3E. And according to my little chart, AX3E, the shape of that molecule, the shape of the AX3 molecule, its molecular geometry would be trigonal pyramidal. Okay. So how do you define the geometry, specifically the molecular geometry? It all stems from, first, the Lewis dot structure. You got to determine the Lewis dot structure. After that, focus on the central atom and be able to classify the electron domains on the central atom. It's all about the central atom. Okay? And from that, that classification, being able to determine number of bonded and lone pairs on the central atom, write the Vesper notation, and then use the given chart to determine the molecular geometry. I also encourage you to use that chart when doing the online homework if MindTap asks you questions about the electron geometry. Again, I won't ask you questions about electron geometry for the exam, but you will have questions on it with regards to MindTap. It's the Vesper notation and molecular geometry portions that you need to memorize. So let's do these 2 examples. I want to know, just for practice, the electron and molecular geometries for the following molecules. Let's start with PCl3. To answer those questions, got to do the Lewis dot structure. So I get my periodic table in front of me, remembering that the number of valence electrons for the molecule is equal to the sum of the valences for the individual atoms. Phosphorus is in group 5, so it contributes 5. Chlorine is in group 7, so each contributes 7. Multiply that by 3 to give me a total of 26 valence electrons. No more, no less, to use in my Lewis dot structure. Next, I determine what my central atom is. Phosphorus is less electronegative than chlorine, so phosphorus is going to be my central atom. I'm going to scatter my outer atoms, my 3 chlorines around it. And now I'm going to start to distribute my 26 valence electrons in the order of single bonds first between the central and the outer atom. So 2, 4, 6. I've now used 6 of my 26 valence electrons. Next, complete the octets on the outer atoms. 7, 8, 9, 10, 11, 12. So that first chlorine is now happy with an octet of electrons. 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. I have used 24 of my 26 valence electrons. Any additional leftover electrons always go on the central atom. So 25, 26, those two electrons are now a lone pair on the central atom, which is phosphorus. Lewis dot structure is done, so it's now time to determine the Vesper notation, which in this case is going to turn out to be the one that we did in the same as the previous example. My central atom represent as A. I have 1, 2, 3 bonded groups, so AX3, and I have one lone pair of electrons on that phosphorus, so AX3E. So I look at the chart for the electron geometry, AX3 represents tetrahedral for the electron geometry, and the molecular geometry is trigonal pyramidal. Let's do this. So let's finish this slide with this next one, XEF2. We're going to do exactly the same thing as we did in the previous example. We got to do the Lewis dot structure. Xenon, noble gas, it contributes 8 valence electrons. Fluorine, another group 7 species. And there's 2 of them. So 14 plus 8. I have 22 valence electrons that need to be placed. Xenon, the least electronegative atom of the two, that will be my central atom. Scatter my outer atoms around it, the 2 fluorines. Distribute electrons by doing single bonds first, 2, 4. Complete the octets on the outer atoms first, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. I've used 16 of my 22 valence electrons. We said any extras go on the central atom. 17, 18, 19, 20, 21, 22. I've now used all 22 of my 22 valence electrons, and you shouldn't be concerned that Xenon has more than an octet of electrons, because remember Xenon from a previous video, it can have expanded octets when bound with a halogen. So that is my Lewis dot structure for XEF2. I can now go ahead and determine my Vesper notation. I have a single central atom A bonded to 2 groups, AX2, and on that central atom I have 1, 2, 3 lone pairs of electrons. So my Vesper notation is AX3E. And that corresponds to a linear molecular geometry and a trigonal bipyramidal electron geometry. Again, don't need to memorize the electron geometries. You will need to do questions about it on MindTap. Focus on the Vesper notation and the molecular geometries for the exam. In class, in lecture, we will do these 2 examples. So we'll do those in class. The next videos will touch upon a few more assets about Lewis dot structures with regards to bond angles, and then we will talk about how to use Lewis dot structures in geometry to determine the polarity of a molecule.